Our final conic section is the hyperbola. You're going to be able to derive its equation. It's very much related to the ellipse. The only difference is that instead of the sum, we're talking about the difference of distances from the foci being constant. Before we get started with the hyperbola, though, we're going to tie all these conic sections together, and I hope you can see after this the commonality between most of them, the parabola being a little bit different. These are all the equations of all the conic sections in what we call the vertex or center format, where the coordinates h, k represent the point at the center of the ellipse or circle, or at the vertex of the parabola or hyperbola. So we started with the circle as a very special form of an ellipse, and the ellipse has this equation, x minus h, the quantity squared over a squared, plus y minus k squared over b squared equals 1, where h and k represent the center of the ellipse. And a and b can be different. Whichever one is larger becomes the semi-major axis. In this case, it would be the x-axis or the a for this particular ellipse. An ellipse that was stretched out more to the up and down would have a larger number under the y. The circle is a very special form of an ellipse where those semi-major and semi-minor axes are equal. We write it like this when it's in its center or vertex form. H, k again being the center of the circle, r being the radius, because r squared is like the semi-major axis and semi-minor axis, which are the same in a circle. So the circle and ellipse very much related. And we derive the equation for a parabola, and it's a little bit different. If h, k represents the vertex of the parabola, the equation is y minus k equals constant term times x minus h, the quantity squared. And that term a represents how far up or down we're going to go from the vertex to both the focus and the directrix of that parabola. So the final conic section we're going to look at is the hyperbola. And a hyperbola can actually be in two different forms, depending on whether it's opening up and down or left and right. And we'll talk about which is which in a minute. But I hope that you can see the similarity between these hyperbolas and then the ellipse equation. In fact, there's only one difference, and that is the minus sign. You'll notice the hyperbola has a minus sign on it, whether it's up and down opening or left and right opening. The ellipse has a positive sign. And that's going to be because of the core difference, that the ellipse is a set of points that represents the sum of the distance from the two foci. The hyperbola is the set of points that represents the difference of the distance between the two foci. So let's go under the hood with a hyperbola. And we'll take that equation, x squared over a squared minus y squared over b squared equals 1. And this is a simple hyperbola with its center at the origin. And we're going to try to solve that for y. What we're going to do first is move this x squared over a squared term to the right-hand side, and we get negative y squared over b squared equals 1 minus x squared over a squared. Well, again, to get y by itself, we're going to multiply both sides by negative b squared, and this is what we get. Y squared equals negative b squared times the quantity 1 minus x squared over a squared. This is what we get. We've distributed negative b squared. So then y is going to be equal, if we take the square root of both sides, plus or minus the square root of negative b squared plus b squared over a squared times x squared. Or, just moving the negative part to the back, plus or minus the square root of b squared over a squared times x squared minus b squared. Here's the graph of a hyperbola that opens up to the left and to the right. And as we've already developed, this is the equation of a hyperbola. And what we're going to do is explore what's happening to the hyperbola as the x values get really, really large. As we move to the far right or the far left, what's happening to the function itself, the y values? As x gets really, really large in the positive or the negative directions, what happens under this radical is this first term gets gigantic because the x gets very, very large, either positive or negative. This b squared term is just a constant, so eventually it becomes trivial, almost negligible compared to that first term. Therefore, the y values, as x becomes gigantic, either on the far right or far left, begin to approach plus or minus the square root of b squared over a squared times a squared, because that b squared, that last little negative b squared, doesn't amount to anything. Which means that the y values at the extremes begin to approach plus or minus b over a times x when you simplify that right-hand side. And that's a linear equation. So that's the equation of the asymptotes what happens at the extreme values of x in the function. And just a reminder from algebra, an asymptote is a line denoting a value the function approaches but can never actually reach. And you can kind of see that starting to happen as this purple hyperbola approaches but does not reach those asymptotes. The equation of the asymptotes is a linear equation in the form y equals plus or minus b over a times x. The one I'm highlighting now is b over a times x. The one I'm highlighting now is negative b over a times x. And these are the equations for the asymptotes of hyperbola, a line that the function will never quite reach. So the next question then becomes, does the hyperbola open up towards the left and right, or does it open up and down? So now we're going to answer the question. No, in no case does the hyperbola ever reach the values of y equals plus b over a or y equals minus b over a. But is it a left and right, or is it an up and down? And the key to the riddle is looking inside the radical. The purple one clearly has a point where y equals 0. So what value would make this inside of the radical equal to 0? And hopefully you can see that if x equals a, then a squared cancels out a squared, and then we get a 0 in the radical. So in fact, this point right here on the x-axis where y is equal to 0, x is equal to a. And in fact, x could also equal negative a because it is plus or minus, and the x term is being squared. So if x were a or negative a, these a squareds would cancel out, the inside the radical would go to 0. So therefore, this is the equation of a hyperbola that opens up left and right. So what does the equation look like for a hyperbola that opens up and down? Well, you may recall from the beginning, we said that a hyperbola could take on one of two forms. It could take on this form, or it could take on this form. In this form, the x term is positive and the y term is negative. Here, the y term is positive and the x term is negative. If you solve it for the other case, you're going to get this equation. And the only difference is there's a plus there instead of a minus. That's because the y term starts out as positive to begin with, so it never becomes negative. So the only difference being a plus there, and that has some implications. And so this is, by the way, what an up and down facing hyperbola would be looking like. The one we derived earlier was a left-right facing hyperbola. So an up-down facing hyperbola has this underneath the radical, and hopefully the first thing you're going to notice is since there's a plus sign there, this can never equal 0. So the y value can never actually equal 0 on an up and down facing hyperbola that's not shifted. And you can see that with this green hyperbola that we have plotted here, this up and down facing hyperbola, that it is never going to get down to a value of 0. It can't. It simply is forbidden because of that plus sign. Even if this x term goes to 0, you're still going to have that b squared term. One way to remember it is that a left-right facing hyperbola is going to have the minus sign in it because the term can go to 0. An up-down facing hyperbola, never going to be 0. In fact, the smallest it can be, if this x term disappears, is the square root of b squared, or b. And so these points are 0, b and 0, negative b. That's really the closest it can ever get to the origin. Because of that plus sign, the up-down facing hyperbola will never reach 0. Because of the minus sign, the left-right facing hyperbola can actually reach a y value of 0. And it does that at the point where x equals a. So let's look at an example. Let's take the equation x squared over 9 minus y squared over 16 equals 1. And by the way, another way to remember whether it's left and right opening or up and down opening is to look at which term's positive. If the x term's positive, it's left and right opening. If the y term's positive, it's up and down opening for the reasons that we just talked about. What happens underneath the radical when you solve for y. So let's try and solve this equation for y. And you could memorize the formula, but I want to go ahead and just solve it for y each time. X squared minus 9 term to the other side, then multiply both sides by negative 16 and rearrange the term so that the positive's in front, and you're left with y squared equals what's in blue there. 16 over 9 times x squared minus 16. Very much like the formula that you developed earlier when you take the square root of both sides, you get y equals plus or minus the square root of 16 over 9x squared minus 16. So we know it opens left and right. The first thing we need to ask is, what is the value of x that will make the whole thing 0? We know that where x equals a, that's going to make it 0. So we're looking for an x value of 3 because a is 3. 3 squared is 9. So if we get 3 in for x, this part will become 16, and this whole thing will go to 0. So we know that the point 3, 0, and oh, by the way, negative 3, 0 are important to this hyperbola. And the parabola is going to be left and right facing from there. So what about the asymptotes? Well, we remember that the slope of the asymptote is negative b over a. And it's negative b over a because we're asking the question, what happens, at the asymptotes, what's happening as x gets gigantic? And remember, this negative 16 becomes trivial when x becomes very large. So when x becomes very large, this becomes y equals plus or minus the square root of 16 over 9 times a very large number. So we can take the square root of that. So the equation of the asymptotes is plus or minus 16 over 9x. When we graph those, it looks like this. Remember, those are asymptotes. Those are values that the hyperbola can never reach. So here's what this hyperbola looks like. X squared over 9 minus y squared over 16 equals 1. It hits the x-axis at negative 3, 0 and 3, 0 because that's where y equals 0. And it has asymptotes at y equals plus or minus b over a, 16 over 9, meaning that it's never going to touch those asymptotes. Let's finish up with an up and down facing hyperbola. We know it's up and down facing because the y term is the positive part. And we're going to even throw in a little bit of an extra difficulty, and that is having a shift to the center of this parabola. And again, it's what makes this parentheses part 0. The shift, the center point of this parabola is going to be at 2, 1. X coordinate of 2, y coordinate of 1. So if we solve this for y minus 1, we're going to get y minus 1 is equal to plus or minus the square root of b over a, 4 over 9, times x minus 2 to the quantity squared plus 4. Since that's a plus sign, we know it's an up and down facing parabola. And the y minus 1 just means we're going to shift the whole thing up 1. And the x minus 2 part means we're going to shift the whole thing to the right 2. So we're going to find the equation of the asymptotes by adding 1 to our normal equation. Normally we'd have plus or minus 4/9 x, but remember it's x minus 2 now because we've shifted to the right 2. And then we've got to bring that 1 to the other side and have the plus 1 because we're shifting it up 1. So the equations of the two asymptotes for this hyperbola are y equals plus or minus 4/9 times x minus 2 plus 1. So we just accounted for that translation to the right 2 and up 1. And we know it's an up and down facing hyperbola, so really all we need is about 1 point, and then we can kind of sketch the pattern for what it's going to look like. So pick a point that makes the inside part of the inside 0. Let's have x equal 2. If x equals 2, the left-hand part of this radical becomes 0, and we get plus or minus the square root of 4, which is either going to be plus or minus 2, but don't forget we have to add 1. So we wind up with the points 2, 3 and 2, negative 1 by putting in that value for 2. That simplifies this a little bit. And we know those points are on the hyperbola, and they're both up and down facing, so now we can sketch what it looks like. So we get something that looks like this, an upward and downward facing hyperbola. So we finished up our conic sections with a review and then an introduction into the hyperbola, a shape that's created by making the difference of distances from the foci constant.